Okay, talk about linear transformations. Okay, I didn't write the word down here, but it's worth writing down. So well, I didn't get to finish the word, but here it is, linear transformations. Okay, let V, let T of V1, V2 be defined as, and this is T applied to the ordered pair V1, V2. And this ordered pair can be regarded as a vector in R2 if we wish. And I pretty much wish that. Then T applied to V1, V2 gives you another ordered pair. And the ordered pair is a linear combination of the numbers V1, V2, the components of this V vector. Your first component. Your second component is another linear combination of the components of V. So it's a simple map. We can easily apply it. And there's a W. We'll get to that in a minute. But let's let V be 2, -3, the ordered pair 2, -3. If you wish, the vector 2, -3. So vector in this direction and standard R2. Let me go ahead and put this camera where it belongs. Okay. So we apply the transformation. T of V1, V2 equals, well, V1 is 2, so we have 2A. V2 is -3, so we have -3B. And similarly, we're going to have 2C minus 3D. Now, depending on the values of A and B, the result here could be any vector at all in the plane. In other words, if I want this vector to equal 7, -42, well, I put 2A minus 3B equal to 7, 2C minus 3D equal to -42. I have two simultaneous equations, and I can easily solve those equations. Okay, if I know my numbers A, B, C, and D, or I can determine numbers A, B, C, and D that'll give me that result. Okay, well, I'm going to get to that. So that's the purpose of our W vector. Okay, so we have this ordered pair. Now I can also write this ordered pair as the matrix 2. Yeah, I've got the wrong numbers here. Okay, I can write these numbers, or I can write this ordered pair as a matrix equation if I regard this ordered pair as a column vector. This would be the matrix equation A, B, C, D multiplied by 2, -3. And maybe I shouldn't use an equal sign there, so I'm going to take the equal sign away. And I'll just say, make a note of the fact that these same components can be obtained from a matrix equation, because this matrix equation gives us 2A minus 3B and 2C minus 3D. We'll talk more about this matrix equation later. Okay, now suppose we want to solve the equation T of V1, V2 equals our W vector. Okay, so let's say we want to solve this equals, well, I said something, I forget what it was, 7, -42, let's say. Okay, so this is a matrix equation. T of V1, V2 equals W. Which equals the ordered pair W1, W2, where now W1 is 7, W2 is -42. If I write out the equation, and I'm going to go ahead and use, well, I'm going to go ahead and write it this way. Okay, so T of V1, V2 is A V1 plus B V2, C V1 plus D V2 equals 7 -42. So we get system of equations AV1 plus BV2 equals 7. CV1 plus DV2 equals -42. This is a system we can easily solve for V1 and V2 because we have two simultaneous equations in the unknowns V1 and V2. Now our solution, depending on the values of A, B, C, and D, might be degenerate. In other words, this side and this side might be multiples of one another. Okay, and it's very possible that this side and this side are multiples of one another, but these two sides are not the same multiple of one another, in which case we get no solution. We could get a solution where each equation is a multiple of the other, in which case we'd have one free variable, we'd have essentially a line of solutions. We'll get to that. So anything can happen over here. We don't know what A, B, C, and D are. Now this could also be written as the matrix equation A, B, C, D multiplied by the column vector V1, V2 equals 7 -42. And I'll just say note this. And this is solvable, uniquely solvable, if and only if this matrix A, B, C, D is invertible. Now, all this we know. Now let's go to specific examples. I want to give this as kind of an overview of linear transformations in R2. And of course, if we went to R3, we could have a V1, V2, V3. We'd have to have, well, we could have anything over here. It could be 2, 3 dimensions. We're not going to worry about that at this point. But we could extend this to higher dimensions. And we would just end up with more components, more equations, and a different matrix. This matrix might or might not be a square matrix. It's a square matrix, then you have a unique solution if and only if it's invertible, and all the stuff that we already know about. Okay, well, that's what we mean by a linear transformation. This is a general form of linear transformation in R2. Any linear transformation in R2 will have this form. You just have to give the numbers A, B, C, and D. And any linear transformation in R2. Now, when I say in R2, from R2 to R2, okay? So transforming a vector in R2 to a vector in R2, and then everything can be set up as a matrix in this way. Now, we're not going to talk too much about the matrices today. We're just going to talk about linear transformations, images, and preimages. So I'll just introduce that notation. This vector we regard as the image of the vector v1, v2. Okay, our solution v1, v2 here would be the preimage of the vector w equals 7, -42. So write that in something that'll show up a little better. Our solution v1, v2 is the preimage of w equals 7, -42. So we have image and preimage. And that's what we want to look at. Okay. So let's say just put this in context. In general, a linear transformation T v1, v2 is going to equal an arbitrary linear combination of v1, v2 for each of two components. We can easily calculate that image either by a matrix or just by doing the arithmetic of the transformation. We can also calculate the preimage of a given vector. We call it W. So we want the preimage of this vector, which is the vector over here that gives us this vector over here. And we see that we can reduce the process of doing the preimage to, well, this equation, which means the first component equals the first, second component equals the second. We get two simultaneous equations. We can solve for v1, v2. Maybe we get a solution, maybe we don't. Maybe we get a degenerate solution, a solution that gives us one free variable. Then down here, we can see that we could also take this system and express it as a matrix equation, as we could for this calculation. Let's do a specific example and then look a little bit at the geometry of the situation. Okay, T of 3, -4, where T of v1, v2 is this transformation where I specified the constants that I indicated previously as A, B, C, and D. Now it's 2, -1, 1, 1. Okay, the image of V equals 3, -4. Well, T of 3, -4 equals 2 times 3 minus -4. And I don't need parentheses, but since I've written it, I'll go ahead and use it. 3 plus -4. And that equals, arithmetic is easy, so I'll probably mess it up, but that's going to be 10. And this is going to be -1. Now we can visualize this image here of the vector v. We can do that as follows. V is a vector 3, -4. So I'm going to write that kind of small, but yeah, so we have 3 here, -4 here. Here's our v. And then we can visualize this as a transformation that takes this vector, and let's go ahead and use a reasonably consistent scale, takes this vector to the vector 10, -1. So if 3 is here, then 10 is going to be 1, 2, 3 times that far, and then a little bit more. So here's 10. Let's say here's -1. So we can project over here. And here's our image. This vector is what we're going to call W. (10, -1). We see that this transformation then has taken this vector and rotated it to this angle and stretched it out. In your homework, in WebAssign, the pictures will often show these two vectors on the same set of coordinate axes. I prefer to think of your vector and your image, or if you wish, your image and your pre-image. However, just to make sure you see this the way you probably see it on your WebAssign, if we're using WebAssign in this particular course, this would look something like this. I'm going to use a slightly different scale. So here would be our vector v. Here would be our vector w. And you see what happens to v. I think you can see it just as well here. But no problem either way. Pretty easy to see what's going on. Okay, now what about the pre-image? Of W? Well, let's just ask ourselves, looking at the geometry of the situation, what if we had a vector W out in this direction, and we wanted to find the vector over here? Okay, now it's kind of unpredictable. You might think by looking at the way this transforms here that to get a vector over here, you'd have to transform a vector that rotates it in some way similar to this. You can't really predict that until you develop some machinery when you can see what happens. In any case, the pre-image of this vector W, and let's say W equals a vector up in this direction. Let's say it's 5, 7. Okay, pre-image of the vector W equals 5, 7. This means we have to solve T of V1, 5, 7. Name things very well here. For V1 and V2. So we write out this equation. So T of V1, V2 is 2V1 minus V2. V1 plus V2. And that has to equal 5, 7. In other words, this is the equation. I should have left myself a little more room, but the equation T V1, V2 equals the W vector. So how do we solve this equation? Well, this implies that 2V1 minus V2 equals 5, and V1 plus V2 equals 7, which implies the augmented matrix 2, -1, 5, 1, 1, 7. We can reduce this augmented matrix and we find V1 and V2. Alternatively, we could write this as a matrix equation. Here's your matrix, and then that's times a column vector V1, V2, and that should equal 5, 7. So you can invert that matrix and calculate. To get the geometry, we might as well go ahead and reduce this matrix. So I'm going to skip a step here, but this matrix, I'm going to switch the first and second column. And there we have it. And I did that just so it'd be easy to get a 1 here. Then I'm going to subtract 2 times the first row from the second. And that's easily done, even though I might screw it up. So watch me. Okay. Well, obviously, if I subtract twice the first row from the second, I'm going to get 0, because that's why I subtracted 2 times the first row from the second. And then subtract 2 times 1 from -1 is going to give me -3. And subtract 2 times 7 from 5. That's going to be -14, and 5. That's going to give me -9. And coincidentally, or conveniently, I didn't set it up that way. I am going to get an integer down here. This gives me 1, 1, 7, 0, 1, 3. And at this point, I could take this another step. I could subtract this row. Well, I might as well subtract this row from this row. And that gives me 1, 0, 4, 0, 1, 3. So V1, V2 equals 4, 3. Now, it was extremely unlikely that when I just wrote down these numbers here, I actually would write down numbers, and this board is, okay, let's clarify it. Okay, this board is a little further over there. I should have checked that. V1, V2 is 4, 3. Now, what does that tell us on this picture? That tells us that if we take the vector 5, 7, and I've got to exaggerate a little bit, but let's say 5, 7 is here. That when we map this by the transformation, we get our target. W was 5, 7, B is 4, 3. Okay. Now I'm going to have to mess up my picture, which I kind of hate to do. Let's see if I can make this as neat as possible, because I find that the Zoom version here tends to really do badly if I have smudges on the board. And I don't know if that's a characteristic of Zoom or my ISP. So this was 3. And now we have the vector 4, 3, which just happens to be perpendicular to the vector 3, -4, worth noting. Okay, that'll be about here. And it looks pretty much perpendicular. That's just pure coincidence. There's no reason it should have come out that neatly. This vector transforms over to our target vector, which was 5, 7. So if there's 10, here's 5, here's 7. So if our V vector is this, our W vector is the vector 5, 7 that we specified. Now note a couple of things. These vectors just happen to make a right angle, which is sort of convenient. Okay, this is a right angle. This angle is less than 90 degrees. So from the obvious connection, or the obvious comparison of these angles, we see that this transformation doesn't preserve angles. Okay, so just a note, a side note, because this is an important thing, do we have an angle preserving transformation? Transformation doesn't preserve angles. That's an idea you just kind of want to get in your head now. It's not going to be in your homework this time, angle preserving, although we could easily do it. You can easily use the dot product to verify this angle is 90 degrees and calculate this angle. The dot product of these two vectors is 50 minus 7. That's somewhat bigger than I would have expected, but it's 43. If you divide by the product of these magnitudes, yeah, you find that the angle, the cosine of the angle is pretty small. It's fairly close to 90 degrees, but it's not 90 degrees, okay? So it's not an angle preserving map. Okay, so bottom line, what you want to see is how to calculate the image if you're given your V vector, components of your V vector, and how to calculate the preimage if you're given the W vector over here. So we were given this vector, we calculated this. We were given this vector, we calculated this. Almost clicked on the wrong thing there. We want to. Okay, now we've seen that if we map this vector by the transformation given here, we get this vector. And if we want to get this vector, we figured out that this is the vector that we would have to map. Now, if all these calculations are done right, everything should work out nicely. If we add these two vectors, we're going to get what? We're going to get the vector 7, -1. Okay, so this V and this V, and it shouldn't be using the same notation for both V's, shouldn't be using a notation W for both W's. So, really what I want to do is subscript this V1 and V2, but then it gets confused with the components of V1 and V2. So I'm going to call this V hat. And I'm going to call this W hat, just to distinguish the two V's and the two W's. In any case, now, if I add V and V hat here, I get the vector 7, -1, which will be out about here. And I wanted to use a different color. I grabbed the wrong piece of chalk. Okay, so if I, do parallelogram or whatever, I get the vector. V plus V hat equals 7, -1. If I add these two vectors, well, again, I can do parallelogram just to see where that's going to be. And it's going to go right through a lot of my labeling, but we know what I've already said, so. Okay. We get this vector, which is our W plus W hat. Not a lot of room to label it, but I'll do my best. W plus W hat equals, well, 15, 6. Okay, now my question is, if I now transform 7, -1, do I get the vector 15, 6? Okay, now, if the transformation is linear, then this should be the case. Because definition of linear transformation, which we haven't given, is that if you transform the sum of two vectors, you get the sum of the two transformed vectors. Okay, so if I transform V to get W and V hat to get W hat, then if I transform V plus V hat, the vector I get is W plus W hat. Now, it might seem obvious that that ought to be the case. Well, that is the desirable case, but it's not always so. There are plenty of transformations I can define that don't do that. However, any transformation where this is a linear combination of V1 and V2, and this is a linear combination of V1 and V2, will have that property. Now, let's just work it out for these vectors. Now, I need to, well, maybe I can remember. Okay. So I've already written a couple of statements. I'm saying that this transformation is linear. I know in advance that if this is a linear combination of V1 and V2, and this is a linear combination of V1 and V2, it will be linear. So I know this transformation is going to be linear, but I haven't proved any of that. I haven't even defined linearity. Okay. Now, there's a little bit more to the meaning of linearity than what I've written down here, but this is kind of the essence of it. That T of your V vector, which I'll call T of V1, V2, and plus T of U1, U2. Now, maybe my notation's getting a little bit confused. Instead of V1 hat, V2 hat, I've used U1, U2. But that's the general way we define it. We don't want to start putting hats and things. If you get too many of them, how many hats can you put on a vector? Or how many tildes or whatever? So I'm going to use U1, U2 and V1, V2 for the two vectors that we start with. Now, V1, V2 on our picture, if you recall, V1 and V2 were 3, -4. And then our vector I called V hat, if its components are U1 and U2, that one was 4, 3. So again, if I transform 3, -4, we know that I get 10, -1. If I transform 4, 3, we know that I get 5, 7. If I then transform this vector plus this vector, which would be 3 and 4, which is 7, 4, -4 and 3, which is 1. Okay, and we saw that. We have these two vectors. I add up to 7, -1. If I transform 7, -1, do I then get the vector, what was it, 15, 6? Yeah, I get the vector 15, 6. Well, let's see how those things work out. I know what V1 and V2 were. I know what W1, which is a transform of V1, V2, and W2, which is a transform of U1, U2 before 3, were 10, 1, and 5, negative 7. So my transformation of V1, V2 is 10, negative 1. My transformation of what I'm calling now U1, U2 is 5, 7. Okay, now see 10, negative 1, and 5, 7, just to make sure we see it. Right there's our 10, negative 1 that we got from this one, our 5, 7 that we got from this one. Is that equal to what I get if I transform V1, V2 plus U1, U2, which is V1 plus U1, V2 plus U2. And I'm going to write that out. This would be the transformation of this vector plus this vector, which is 3 plus 4, negative 4 plus 3. Okay, so here and here are these components, which are these and these. So you can think through this expression gives you this. And of course, then that would be T of R7, negative 1. And remember, 7, negative 1 was here. So we're seeing if transforming this 7, negative 1 will give us our 15, 6. Well, if we transform 7, negative 1, we get 2V1 minus V2. 2 times 7, I guess I better write it out. 2 times 7 minus negative 1, and 7 plus negative 1. Well, lo and behold, that equals 14 minus 1 gives us 15, and 7 and negative 1 gives us 6. Well, what were we checking? We checked if we transform this vector, do we get this vector? This vector being the sum of these two, we transform it, do we get the sum of the two transformed vectors? Well, the sum of these vectors is easily seen to be 15, 6. And that's exactly what we wanted. Okay. And I probably should have noted that T of V1, V2 equals this. T of U1, U2 equals this. Okay, if I add these two vectors, I get this. And now if I transform the sum of these two vectors, that's exactly what I get. Okay. Now linearity. Means the T of V plus U equals T of V plus T of U. Make sure you understand what that's telling us in terms of the example. Also, t of some multiple of v is equal to that multiple of t of v. Now that kind of follows from this, but we generally list it as a separate criterion for transformations. If the transformation is linear, it can be represented by matrix in a way that I've already pretty much demonstrated. Now there's much more to this, but that's sort of the essence of the connection between linear transformations and matrices. And of course, if it can be represented by a matrix, then you can define a linear transformation just by a matrix. Representation and the linear transformation itself are, in a sense, identical, or isomorphic, or they can be identified with one another. Doesn't matter which way you represent the thing. Okay, our next question is, if we know what t does to the vector 1, 2, and to the vector negative 2, 1, in other words, what does t do to two different vectors? And if we assume that t is linear, then if linear t of v1, v2 equals av1 plus bv2, cv1 plus dv2, for some v1 and v2. Now for some, got to get out of the habit of writing things without thinking ahead to what I want to do next, and writing down something that doesn't make sense. Okay, for some A, B, C, and D. Okay, well, for these conditions, t of 1, 2 would equal A times 1 B times 2, and that would equal 3, negative 4, so that A plus 2B has to equal 3, negative 4. So that has to equal 3, and 2B has to equal negative 4. And then T of 3, negative 4 has to equal A times 3 And pretend you didn't see me do this. It wasn't making sense as I wrote it down. And I'm glad that I at least saw that it wasn't going to make sense. Again, writing something down and not thinking ahead. Sometimes you can't win. Okay, so let's write this out again. T of 1, 2 by the rule would equal AV1 plus VBV2, which is, I'm just going to write it out, A plus 2B, V1 being 1, V2 being 2. You got the A plus 2B. That's your first component. And your second component is C plus 2D. And of course, now that has to equal 3, -4. So that A plus 2B is 3, C plus 2D is -4. T of 3, -4 equals, well, 3 times A plus BV2, which is -4 times B, and 3 times V1, 3 times C, -4 times D. And that has to equal 5, 1. So 3A minus 4B equals 5, and 3C minus 4D equals 1. Now we have 4 equations and 4 unknowns. So we can write down the 4 equations. And then we can write these 4 equations in the form of an augmented matrix. And we note that again, I've written something down that makes no sense. Hopefully you saw that before I did. I was going to get an immediate conclusion that if you add the first 2 rows, you get 0, but I was looking at that alignment and wrote it wrong. So let's write it correctly. So this would be 1, 0, 0, 0, 3, 1, 2, 0, 0, -4, 3, -4, oh, and I did it again. And I'm still not writing it down correctly because I'm just not being careful. Apologies. Okay, so you get something going haywire in my brain here. Hopefully your artificial intelligence program doesn't do this to you. Okay, so 1, 2, 0, 0, 3. In other words, this column's for A, this column's for B, this column's for C, this column's for D. So then we get 0, 0, 1, 2, -4, because now it's C and 2D. There's our C column, our D column. And then we have 3, -4, 0, 0, 5, and 0, 0, 3, -4, 1, and I finally got it right. Okay. Now this matrix can be reduced. The first step will be to get this row and this row next to each other. So we're going to have the 1, 2, 0, 0, 3, and the 3, -4, 0, 0, 5. And we can see immediately that anything we do, multiplying, and any row operation is going to leave the zeros here. So essentially, we just got to work with these coefficients. So if I subtract 3 times the first row from the second, I eliminate this, and I immediately get an equation I can solve for B. And then I can use that to solve for A, and everything works out pretty quickly. Okay, so my main point that I've been trying to get to is that you can do this rearrangement. Kept writing down things wrong, and again, apologies, but that happens. Okay. Now over here I have 0, 0, 1, 5 and 0, 0, 3, -4, 1. And notice I have the same numbers. And you can trace back here and see how that happened, but it turns out to be really pretty easy to reduce this matrix. Now, the difference is that the numbers I have here for these 2 rows are different than the numbers I have here for these 2 rows, so that my A and B are going to be in certain proportions and so forth, or C and D. But since these numbers are different than these numbers, I get just about anything. Well, I'm going to leave the rest of it to you. But looking at it, it looks like I'm going to get C equal to -6/5, 5/6. And I'm not going to do that in my head because I'm not sure about the 5/6, but I think that's maybe right. Okay. So what I've done now is I found my A, B, C, and D, so I can write out my transformation with the numbers A, B, C, and D, and now I have a transformation that I can do anything I wish with. Okay, well, that's the idea. Okay, well, there's more, and we'll come to it a little bit later.